Right. Hello, everybody. We've got our practice quiz here. We're going over logarithms and some exponential stuff. The first two questions are basically just trying to tell the difference between two different situations that we run into when we're dealing with exponential functions. Sometimes we run into situations like this, other times we run into situations like that. And they look really familiar, or they look really similar, I should say. There's kind of four different pieces, and we know three of them, and we want to know the fourth piece. The question that you have to ask yourself is, how can I figure out what the variable is when it's an exponent versus how can I figure out what the variable is when it's a base? Okay. And this one down here on the bottom is more familiar. You've been solving that sort of stuff for a while. Things like x squared equals this or x cubed equals this. This is a situation that you already knew how to solve before you ever heard the word logarithm. Use a root. In this case here, where the 40b to the 10th, you would divide by 40 and then you would use the 10th root. So that's when you have an unknown base. When the base is unknown, you use a root because you know what root to take. You take the root that is the inverse of the power. If the power is 10, you're taking the 10th root, which is equivalent to the 1/10th power. You use a logarithm when you don't know what the exponent is. And one way to remember this is that in order to use a logarithm, you need to specify what the base is. You need to say like log base 3 of both sides or natural log of both sides, which means base of e. And so if you know the base, that's the only way you could ever use a logarithm. You need to know what the base is to do a logarithm. Similarly, you could only ever do a root if you knew what the power was. So try to keep that straight. I know they look alike, but they are different situations. What we're doing here is just converting, rewriting it in different forms. The thing to keep in mind is that if you have an exponential equation, then you also always have an equivalent log equation. These two here are the same equation. They aren't really different equations. They are the same equation, just like these are the same equations. Like x minus, let's say, b equals a is the same equation as saying x equals a plus b. Those are exactly the same equation, just like the exponent and the logarithm one are the same. So here I can say that t is log base 0.85 of 0.58. This one over here, there's a 2 on the bottom, so I can say it's the same as 2 to the n over 20. The key thing to keep in mind is that whatever your base is always on the bottom. Don't think about anything else. Base stays on the bottom. That's all you need to remember. So when I look at any sort of problem like this, whatever I see as the base, I keep it on the bottom. The other two people just switch sides. Base is e, so I use the ln. That implies a base of e, so the ln of f is equal to y. Okay. Now everything, when we're on the next section where we're doing properties, everything that happens with exponents has a mirror image that happens with logarithms. And that is because of this idea right here that logs and exponents are just inverses of each other. So for example, we know that multiplying with exponents becomes adding inside of the exponent. And if you switch that around to logarithms, that means you know that multiplying inside of a logarithm has to switch to adding between two logarithms. It has to do that. Similarly, subtracting, dividing exponents becomes subtracting, and so so dividing inside of a logarithm becomes subtracting. I kept saying it out of order from how I'm writing it. And then the last one is that when you have a power to another power, you can multiply those powers. And it's the same sort of idea with a logarithm. If you're multiplying out front of a logarithm, you can make that a power inside of a logarithm. So number one becomes natural log of 2 plus natural log of x to the fifth minus natural log of y. I made the multiplication into addition. I made the division into subtraction. The last step that we do want you to do when you see this sort of problem, we want you to bring the power of 5 to be multiplication in front. Let's try to box off this last one here. That ln means log with a base of e. This log means log with a base of 10. So we have the log of the square root of x minus the log of 4 minus log of y to the 5th. Because we're dividing by 4 and we're dividing by y to the 5th. The square root is the same as the 1/2 power. So 1/2 log x minus log 4 minus 5 log, and there's a y squeezed in there. All right, let's move down a little bit. This is going backwards. We're consolidating into a single log. So I'm going to put the 2 as the power on x, the 3 as the power on 4, the 4 as the power on z, and then there's no power on d. And so I can make this the natural log of x squared times z to the 4th, because those were the two positive terms. Positive powers stay on top. And on the bottom we have 4 to the 3rd times d. Negative powers go on the bottom of the fraction. So negative logarithms go on the bottom of the fraction, because logarithms and exponents are really the same thing. Here we have a little word problem. A place in southeast Grosvenor, 1951, population of 1,100 dangerous beasts was growing 1.8% each year. Assuming the same rate, what was the dangerous beast population in 1955 or 1946? So here's our equation. I guess I could use the number. The number of beasts is a function of years, where you have 1,100 to start, and it grows at 1.8%. So I saw some of you write 1.18. If you write 1.18, you're telling me it's an 18% growth. That's a lot of dangerous beasts. So you got to watch out for that. 1.018 would be 1.8%. And this is raised to the number of years. And I'm just saying that this is the years after 1951. So just be careful with that. So for 1955, that's 4 years after. And so that's going to be, just type it and see what happens. 1,100, 1.018 to the 4th. So that's what I typed in. So we get 1181. And 0.36, I'm just going to round it down. I don't know exactly what type of dangerous beasts these are, but I don't think you could have 0.36 of them. 1946 is 5 years before 1951. You just subtract them to get that -5. 1946 minus 1951. So I'm doing this and I'm raising it to the -5 power. So your calculator should look like I did there. And so that comes out to be about 1,006 dangerous beasts. Okay, and let's see. Now we're working on completing a table here. Setting it up algebraically. So in this table, each of these is a separate situation. Each row is a separate situation with a different piece that's unknown. So keep in mind what we asked you at the beginning, where we either have to find the base that's unknown or the power that's unknown, or here we have one other situation, the initial amount that's unknown. So in this first one, we don't know the initial amount. So we don't know the initial amount, but we know, I believe that this copied badly. I think we're going to go with 6.1%. Okay, so we know it's 1.061, not 0.61, because that'd be 61%. Number of changes is to the 8th, and that's going to equal the final amount of 8,000. I want you to notice that 1.061 to the 8th power is just a number. It's just 1.6-ish. So you just have a times 1.6 equals 8,000. Well, so you just do 8,000 divided by the previous answer you had in there. Dividing cancels multiplying. Sometimes when we're doing this logarithm unit, people forget about solving by just dividing. They think they have to do a logarithm or something like that. Okay, so we end up with 4981.58. And the overall percent change is taking the final answer and dividing it by the first answer. And I want you to notice something. We already knew that answer, 1.605606. And that is a 60.6%. How did I do that? I did 1.606, took away 1, multiplied it by 100%, and got that percent change there. Okay. Next one, we know the initial amount. We know that we lose 2.5%. So you're going to multiply by 0.975. We don't know the number of times. And we know that equals 450. Here we are going to have to use a logarithm. So first we go 450 divided by 500, get 0.9. And then we do the log with a base of 0.975, okay? So we have 0.975 to the x equals 0.9. So we're taking the log of both sides of the equation because that cancels out the base. Notice that the base stayed on the bottom, 0.975 stayed on the bottom, so we get 4.16. What's the overall percent change? 450 divided by 500 is 0.9. We already knew it was 0.9. And so that's a negative 10% change, lost 10%. On the third row, we know the initial amount. We don't know what it changed by. We don't know the percent change. So we're just going to put here the b because I don't know what the base is, but I know it went to the 10.9 and equals 500. So I go 500 divided by 800. And this time I'm not going to do a logarithm. I'm going to do a root. I'm going to do the 10.9th root. Remember that roots are the same as fraction powers. So I could have done the 10.9th root, or I could have done the 1 over 10.9 power, and that's my base 0.957. But we have to be careful because we want a percent change. So what I'm going to do is subtract 1 from that. You get negative 0.04. So that means I'm losing like 4.2% loss. And then the 500 divided by 800, we did that calculation right up there. 0.625 is a 37.5% loss. Okay, almost done. Basically the same idea on this next one. 50 base to the fourth equals 56.8. So I go 56.8 divided by 50. Get that number. Raise it to the 1/4 power. I could do the fourth root. It works the same. I get that number. 1.032 means 3.2% gain. And overall change was 1.136. We already did that. So that's 13.6%. It's positive because it's going up. Last one, 4,000, 16% unknown number of times equals 8010. So I go 8010 divided by 4,000. I get that number. Then I'm going to do the log with a base of 1.16. Math, alpha math. 1.16 is my base of the answer I just got, 4.68. Overall percent change is 100%, 100.25%. And I got that by looking at the right there, the 2.0025, and then subtracting 1 from it, just like I showed in the earlier example. All right, last one. We've got an equation. We can use our log rule to bring together that it's 5 times x minus 19. Addition becomes multiplication. We can change it to exponential version by getting rid of the log base 2. So I have 5 times x minus 19 equals 2 to the 6th, which is, I guess, 64. Then I can divide by 5, and I get 12.8. And then I can add 19, and I get 31.8. And that's it. All right, let me know what questions you have. Thank you for watching.